it seems like the birth of our universe and its constant evolution might not be as well understood as scientists used to think it was. There seems to be a growing problem troubling most cosmologists, and it might even cause a massive shift in the field of cosmology as we know it. Some might even call it a crisis in cosmology, and they have a valid point. So join us today as we dive deep into this puzzling situation and talk about the crisis in cosmology, which might cause a huge shift in the understanding of the cosmos as we know it. Have you ever wondered how massive celestial bodies come into being? How do a few clumps of dust form entire planets? Well, scientists have been studying this type of formation. More precisely, they have been trying to understand how matter seems to clump together in space, forming asteroids.
Somehow it will have to grow from dust to solid rock.
Giant objects like planets, as well as galaxies and superclusters. This might seem somewhat simple, but in reality this question has baffled scientists multiple times. When dealing with massive calculations based on the workings of our universe, cosmologists and astronomers work with something that is called the S8 parameter. Sigma 8, or S8 for short, refers to the lumpiness or clumping of matter together. S8 parameter can be measured through redshift, a phenomenon in which we study the change in frequency of light as an object is moving away from us. Low redshift observations like weak gravitational lensing, where a black hole is used as a lens to distort light from exceptionally far distances, are used to measure the precise S8S value. This works just like how a telescope is used to zoom in on faraway objects. Another way of measuring this is through the Standard Model by using the cosmic microwave background, CMB, which is the radiation and heat left over from the Big Bang. Now this is where the real head-scratcher begins. It turns out that the results derived from the cosmic microwave background experiments give a much higher S8 value than the low redshift method. What's even more perplexing is that we don't even know why. How is it possible to get two different readings when measuring the same property? This newly rising issue is causing a massive stir in the cosmological world. This difference in the S8 values is called the S8 tension, which has caused the cosmological community to be dumbfounded to a serious degree. This major gap in our understanding of the universe has caused some scientists to question the validity of everything that we currently know. In the past, scientists faced a similar issue named Hubble Tension. The Hubble Tension first became apparent when scientists tried to understand the constant expansion of our universe.
When Hubble was launched, one of its main objectives was to measure the Hubble constant, the expansion rate of the universe.
Charlie? Yes, boys, stand by for a go for release. Minute late. Okay, Charlie.
Flight PDRS.
Go ahead.
The telescope's released.
Okay, thank you.
From the very first day after it came into being, the universe is expanding on a constant basis, and even with today's modern technologies, we're still unable to find the accurate answer behind this continuous expansion. The rate at which this universe is expanding can be signified by a number called the Hubble constant.
We know that the universe is expanding. We've known that for almost 100 years. The rate at which the universe expands is a number we refer to as the Hubble constant.
Now, the Hubble constant can be measured through two different methods as well. One of those methods used the same cosmic microwave background radiation to understand how fast the universe is expanding. Another method is through studying standard candles, which uses the information that we currently possess about Type 1, a supernovae. Specifically speaking, it actually measures how bright they are. By measuring their perceived brightness and comparing it to how bright they should be at their current stage of life, we are able to calculate the Hubble constant. And just like the S8 value, the Hubble constant is significantly different if measured through both these methods. Even after almost a century of astronomical calculations and observations, scientists cannot seem to agree on a true value of the Hubble constant. A singular value, which can be proved through different methods of observations, might help us understand various laws of physics that govern our universe from a much deeper perspective, such as dark matter, dark energy, and other theorized forces which contribute to our ever-expanding universe. So why are there such huge holes in our understanding of the universe? Is it because we hold a bias towards our current knowledge, which might be flawed? Or is it because our human brains aren't able to comprehend this complex information and make sense of it? Problems like these symbolize that we are nowhere near understanding the entire nature of our universe, and the puzzle we desperately try to solve still has a few pieces missing. Scientists recently tried to find the missing pieces regarding the S8 tension by using the largest computer simulation of our universe, called FLAMINGO. FLAMINGO is a huge acronym which stands for Full Hydro Large-Scale Structure Simulations with All-Sky Mapping for the Interpretation of Next-Generation Observation. What a mouthful. Not only is this the largest ever simulation, but it also takes into account the entirety of our universe from 13 billion years ago till today. To understand how impressive this simulation really is, you first need to know that it required a total of 50 million hours of computing time, distributed among 30,000 processors of the supercomputer in Durham University. And to set it apart from other large-scale simulations, FLAMINGO also took into consideration other universal properties than gravity. Baryonic matter, which only contributes to 15% of the mass in our universe, as well as cosmic neutrinos, particles which carry extremely small mass. Now, since this is a state-of-the-art simulation that considers almost every cosmological parameter that was not considered before, you might think that we would have gotten the answer to our S8 tension problem, right? Not at all. In fact, this has caused the problem to escalate even more. This extremely powerful simulation has no way to solve the very question it was designed to answer, and this has caused scientists to consider changing the entire standard model of cosmology as a whole. We might have missed something immensely important in our quest for knowledge, or maybe let a few biases enter into our problem solving. After running 28 different simulations on FLAMINGO, all done with minor adjustments made to different parameters, we still cannot justify why we do not have an answer yet. To add even more complexity to this already very convoluted issue, various space probes have been launched in order to study these matters much more closely. One of the most famous of these space probes being the James Webb Telescope. Unfortunately, the deep field images captured by the James Webb Telescope have caused an even bigger stir amongst the astrological community. From what it observed, the distribution of matter is still much more clumped together than what the simulation tells us. The direct contradictions of the James Webb Telescope acts just like putting gasoline on top of a raging fire. The biggest issue that stems from all of this uncertainty is that scientists are questioning the very highly regarded theory of gravity itself. Now, there are some explanations that some scientists have denoted might be causing this issue to occur, but nothing as of yet has been pinpointed as a solid experiment-based answer to this head-spinning question. One way of trying to explain this is simply by calling it an effect of dark energy. Maybe dark energy itself became much more powerful over time, due to whatever reason, causing the universe to be pushed apart much more than we believe it to be. If that's the case, then it can somewhat explain the problem that we discussed earlier, called the Hubble Tension. Conversely, another reason that might be causing this troublesome scenario is the idea of galactic winds. Galactic winds are powerful forces exerted by massive black holes. We also are keen on the knowledge that extremely powerful emissions radiate from the center of galaxies as they are forming, which causes matter to be pushed apart even more. This was the first idea shared by scientists in order to explain the S8 tension, but it still does not fully equate into the complete issue, nor does it provide a semi-understandable reason for them. Obviously, we can always pen it down as a miscalculation that might have gone unchecked, but I believe that to be highly unlikely. Does this piece of information suggest that it's all bad? Clearly no. In reality, this is bittersweet news. The sweet part of this information is that this is how science works, through revision and revamping of older concepts into newer ones until everything fits together snugly, like a metaphorical puzzle. However, some extremely cherished ideas might get thrown out the window, and that's what is causing the major buzz. Whatever this change may be, I know for sure it will be for the better understanding of our entire universe, something that all scientists will agree is a positive change in the long term.